Okay, so I think we can start. So till now in this course, we have talked about how to do reliability analysis, different methods for doing reliability analysis, and after that we have talked about reliability based design optimization and robust design optimization. I mean, in a nutshell, you can say we have talked about design under uncertainty. So if we look into the reliability analysis method that we have talked about reliability analysis methods in more or less three categories. The first category was based on Taylor series. There you have the form, you have the SORM, and you also have HORM, which is not something we have discussed, which is not something that is in the syllabus, but that also comes under the same category. So you have the first order reliability method, you have the second order reliability methods, right? And the idea is very simple, that is based on primarily working in the standard normal space, and that is based on finding beta, which is distance of a point from the origin which is nearest to the origin but is on the limit state surface, and then about that you try to form your Taylor series approximation. It can be first order, it can be second order, and that's all, right? That is what we have discussed, and that was the first class of method we have discussed. The second class of methods that we have discussed is based on sampling, is based on the law of large number. But the idea is you will draw lots of samples and then use those samples to calculate the probability of failure directly. You do not go the reliability index route, but rather you calculate the probability of failure. And in sampling based approaches, we have talked about Monte Carlo simulation, we have talked about importance sampling, we have talked about subset simulation, and that is all. There is also Latin hypercube sampling, we have not talked about that. And then, but the problem is that the Taylor series based approaches were less accurate because of the Taylor series based approximation. The sampling based approaches were more accurate but significantly more expensive because of the fact that you need to evaluate a lot of samples, and evaluating one sample might mean running a finite element solver, right? So these are the things we have discussed in the first two sections. The third section, the third module was about surrogate based approach, where the idea was that we want to do Monte Carlo simulation, but first let us build a surrogate model, a cheap emulator, and then use the surrogate model to do Monte Carlo simulation. And that allows us to do a lot, I mean, sampling very fast. But the idea is that if your surrogate model is accurate, your results are accurate. If your surrogate model is not accurate, your results are not accurate. And in surrogate based approaches, we have talked about the response surface method, we have talked about the polynomial chaos expansion, we have talked about the Gaussian process, and there are others. We did not talk about it, but there is neural network, there is RBF, there is antibody composition. We did not talk about that, right? But there is one more important part in surrogate model that we spent one lecture on, which is the design of experiments, which allows us to draw samples, training samples, in a way that is going to assist the surrogate model to learn the underlying limit state function from the minimum, hopefully minimum or less number of samples. And that is what design of experiments is all about. After that, we go into RBDO and RDO. I'm not going to that, but these are the things we have discussed, right? But in all of this, we were working with systems that was having only one performance function. We were working with function that was having only one limit state function, the same name, which means we are working with systems at a component level. So basically what we have discussed till now is only component reliability analysis. So till now, so Till now, we have only discussed or solved reliability analysis problems with a single limit state function. We have not solved any problem that was having more than one limit state function, right? Right? But what do you think in real life? In real life, do you think systems has only one limit state function? Never. All systems can fail in multiple modes. For example, if I take a cantilever beam, it can fail because the deformation is more than some pre-specified value by the codal provisions, but it can also fail if there is if the, let's say, the stress exceeds certain value. It can also fail if the moment exceeds a certain value. It can also fail due to buckling. So it can also fail because of generation and propagation of crack. So any real life system you can imagine, even a simple cantilever beam, that's probably the simplest one, right, always have multiple failure modes. It is seldom that you will be dealing with a problem that has only one failure mode, right, which means system reliability or handling multiple failure modes is not something we can avoid. And we cannot do anything realistic unless and until we have tools and techniques and methodologies and algorithms that can handle multiple failure modes, right. So all physical systems have multiple failure modes. Okay, modes. And when I write failure modes, you should keep in mind that each failure mode is supposed to give you one limit state. I mean, you can, that can be, right. It can, yeah, that's how you should think of it. So each failure mode should give you a single limit state. Okay, lib. Okay. So each failure mode is supposed to give you a single limit set, right, which means we are handling multiple failure mode means handling multiple limit set function. That is what it means, right. Okay, so all physical systems have multiple failure modes, and so we need techniques to do that. System reliability allows us to handle multiple failure modes. Okay, so that is what system reliability is all about. Okay, now this multiple failure mode can also become multiple component level failure, and all of those things will come to that. So right now the definition I am giving is based on this motivation that we have multiple failure modes, but you will see that soon that multiple failure mode can mean different things, and we'll talk about it. Okay, so system reliability allows us to system handle multiple failure modes, or rather system reliability is about handling multiple failure modes. You can also think of it like that. Okay, any doubt on this? This is clear? So this is clear. Let us take two examples and try to understand what failure mode might means and how those failure modes can help us in finding the probability of failure of that system. So let us take two examples and let us together try to come at a conclusion that how these failure modes will be combined to find out the reliability of the system. Okay. So examples, right? So let's start with problem 1, or rather example 1. And this is our problem that we have solved earlier. So let's say that I have a cantilever beam subjected to some point load. Okay. Subject to some point load. You can also assume there is some axial load, but let's not go there right now. Okay. A simple problem, undergraduate level problem, I will say. Now, for such a problem, what are the different types of ways it can fail? Can you think and tell me? One is obviously deflection. So one will be like, let's say G1 of x less than 0, and let's say this is because of deflection, right? And in this case, we have already seen PL by 325 minus PL cube by 3EAI, and using that we can form that, right? Anything else you can imagine? Crack formation, how will you write something for crack formation? So let's write G2x is less than 0 denotes crack, but how will you do that? No, how will you define fracture energy once? He will say better, I guess. So anything else? Fracture energy is one way, that using the fracture energy or toughness, fracture toughness is also there, right? You can think of such measures, some material properties, and if that is exceeded, you can say that it has failed. You can also, I mean, some will say that the fact that there is a crack is a failure. Forget about crack propagation. The fact that crack has generated itself is a sign of failure. Some might say that. But then those who are working on fracture mechanics will say that all systems have crack. It's just micro crack you cannot see. Right? So then comes the size of crack, the depth of crack, the location of crack. So you can think of even within that single limit state, it can be multimodal. Right? There can be multiple way of representing that, and those might not be same. There is the Griffith criteria, there is the stress-based criteria, all of those things are there. So this tells you how when the crack will propagate. So one can say that okay, cracks are there, that's fine. The moment it starts propagating, it's a failure. Then comes the Griffith criteria, the all the crack propagation criteria, right? That comes into picture. So it can be based on energy, based on stress, and all of those things can happen. Anything else? Creep, correct. So creep, like if fracture is one, then fatigue should be another, creep should be another. So actually fracture in most cases will be because of either fatigue or creep. So these are not decoupled. Fatigue induced fracture will happen. Creep, because of that also it can happen, right? Creep, okay, I will keep it at G2 only because they are of similar types. Anything else? Buckling. If it buckles, you can give axial load. Why do you assuming there is no axial load? And can you not do a buckling analysis for a transverse load? You can. Even for you use abacus and you can do in there. Yes, it will not be the predominant mode of failure probably, but it can still happen. Right? Buckling can happen. If the load is proper, twisting or torsion can come into picture, and all of this thing can happen. I mean, in a realistic scenario, this load will not be like this, right? This load can be at some angle or so. So buckling can be one of the ways, right? Anything else? Joint failure. That is, along with fatigue, joint failure is one of the most common form of failures. Most of the failures start at joints. Joint failure, right? So you can imagine, right? There are different failure modes that are there, even for a simple thing like this, right? So let's write G3 as the joint one. Now how will I define joint one? Let's say at the fixed end, a moment will be generated. If that moment exceeds a certain limit, the joint can only withstand certain amount of moment. If the bending moment at the fixed end exceeds that limit, we assume that the joint has failed. That's a valid one. So let's say this is it for joint. And there can be many other. I'm not writing those. Okay. So now this is one example. Okay, we'll come back to this, but let me tell you a second example. We'll come back to this after I have written down the second example. Problem 2. Let us talk about water supply in your house. Okay, so suppose there is a city. Okay, in a city you have a house, and there will be water supply pipelines all over that will come. Now, what are the different ways water can be supplied to your home? And sometime all of those exist or some of those exist. Way number 1, you have a well in your house. Because of the well being there, water comes from underground, and that becomes one source. So let's say the one of the source is well. So if it is too hot, the well dries up, the pump cannot bring the water up, that's a failure mode, right? Second one can be that there is some water supply unit in a municipality that supplies water, let's say twice in a day at some given time, and that forms your second failure mode. That if for some reason the municipality is not working, and because the municipality is not working properly, water has not been supplied. It happens, right? Sometimes notice comes that today water will not be supplied, right? Very common. Third mode, let us assume I don't need a third mode, but I was going to say river, that there is a river nearby, and if you really want, like old days, you can go and collect water from there in the extreme scenario when nothing is there. So that also can be a mode of failure, right? But I'll not go there, but that can be, that can be, right? There is a fourth one also. When the water gets supplied, you store it in your tank, right? Now someone has a big tank, someone has a small tank, and all of this happens. Somehow the tank has leaked. That's a mode of failure. One is water was not supplied. Second one is water was supplied. You stored it, but there was a leakage. So that is, let us write that one, which is tank. Okay. So this is my problem 2. Problem 2 is clear. Problem 1 is clear. So now tell me, problem 1, we have a system. The system is a cantilever beam. When will I say that the system has failed? Any of this, right? If either it fails because of deflection, the system has failed. If it fails because of crack, the system has failed. If it fails because of joint, the system has failed. And if it fails for any of those, the system has failed. You agree? Such a system is known as weakest link system, because it will fail through the weakest link, or the series system, where if something fails, the system fails. Okay. And for such system, you can imagine the probability of failure will be higher, because if these modes, by the way, these modes need not be independent. Because of large deflection also crack can generate, so first two becomes dependent. So there is, these modes are independent is a very big assumption. But if I assume that the modes are independent, okay, and then you can find out the joint failure as union of these 3 events. And we'll talk about that later, but right now I'm just saying union of these 3 events, A union B union C, which is equal to, we'll write down it in the form joint A plus B plus probability of A plus probability of B plus probability of C minus AB minus BC minus CA plus ABC. So something like that you will write. And then if they are independent, you will use that to write AB as A times B, ABC as A times B times C. Now each of this you have found out using your component reliability analysis. Use those Substitute those to find out your system reliability. So the message I am trying to give is that it is true that no system has a single failure mode. But to find out failure probability because of multiple mode, you first need to find out the probability of failure for each mode separately and then combine them. That is why we spend majority of this course talking about component reliability, because without component reliability, system reliability does not exist, right? So this was a series. Next one. A failure scenario is what? When water is, I do not have water to use in my house. That's a failure scenario, right? In this case, when will that will happen? When all of them are true. You don't have water in your tank, water is not supplied by the municipality, and because of some reason the well has dried up, or you cannot take up, use the water of the well for whatever reason. So when all of these failure modes happen, then only we will say that this system has failed. So this is a parallel. If that was series, this has to be parallel. But this is also known as the redundant, because you have redundancies. Even if one fails, you have backups, redundancy, right? So this is known as parallel system. Now the series and parallel systems are actually two extremes. Real systems are neither series nor parallel, they are mixed. Some portion might be series, some portion might be parallel, right? And yeah, so these two are kind of extremes. This is the safest one, because in this case the system will fail when A and B and C all fails, which is probability of A intersection B intersection C. Again, assume them to be independent, which is a big assumption. We should not do that, but let's do that, which is equal to probability of A multiplied by probability of B multiplied by probability of C. Now each of this is a number between 0 and 1, which means when you do a product, the number becomes smaller. Whereas in last case, we were adding things up, they were becoming bigger. I mean, they were also subtracting, but in most cases that will be bigger. Okay, so this is an example of the parallel system. Okay, so this is a parallel system. The other one is a series system. Any doubt on series and parallel system? That is the biggest challenge. And generally what you do is that in most cases you will not know the correlation between them. So what will you do? You will do the two worst case scenario, or two extremes. One is you assume them to be uncorrelated, find it out. Second one, you assume them to be perfectly correlated. If one fails, other will fail. Find it out, and that will give you a bound. In system reliability, you will see in the next lecture, not today, that we do not get, in most cases, a probability of failure. We get a bound of probability of failure with these extreme scenarios. If you know the exact correlation, then it's fine, then you can do that. But in most cases, you will not know that. What you will have to be happy with is knowing the bound of in which it can be there for the two extreme scenarios. And then there is first order bound, second order bound, and all of those things. You can come up with your higher order bounds. Almost impossible, because you can probably do it for 2-3 modes, assume 100 modes. Gone. Okay. And in most cases, it will be 100 modes. Okay. Even the systems I have shown are very small. I will go to a larger system now in a short while, but these are not even systems, these are components. A cantilever is a component. Even that is a system reliability. Now, in a house, the cantilever is a balcony. So that balcony itself is a system. Now there are beams and columns, each of this is a system. So you are looking at system of systems. Each of those can fail in multiple modes. When will the building fail? That is the real problem. And that is where we are going. You can imagine how it will look in reality. Okay. And you can easily imagine that that is not a series, that is not a parallel system. A building system of systems is neither parallel nor series. Some will be, even if all the individual components are series, the overall system is something else, right? So we'll go there. Okay. But this was system and parallel, and this was kind of two extremes. But in general, in a system reliability, what are the things you need to be careful about, let us say? Or what are the things you need to be aware of? In system reliability, one needs to consider, in the ideal world at least, the following. Let us see what are the things. One is you have to consider different failure modes. That should be clear by now. Everyone agrees that in system reliability we need to consider different failure modes. That is the first thing, and that is what we have already discussed. And we have seen that how they can combine. Failure modes. The second one is redundancy. Now I gave you some idea of redundancy, but that was nothing. We'll go to that now. And there are other points, I'll write them later. I'll go one by one and come back and write them. Okay. Redundancy, right? The cantilever beam we were talking about, let us take that. But now it is not a cantilever, it's a propped cantilever. Everyone knows what is a propped cantilever, right? I mean, again, UG stuff. Imagine a load now has to be shifted. So let's say the load is here. What are the different modes it can fail? We took 3 previously. Let us take 2 out of those. Okay. G1 is maximum deflection, so it is in terms of deflection. Okay, I'm not going to crack because, and G2 is the joint. So G2 is the joint, and not just any joint. Let's say joint number A. This is joint number A, and then this is how it will look if I draw the free body diagram, right? And this G2 is in terms of moment. So moment carrying capacity minus moment generated should be less than 0. Capacity minus demand. When I say moment, it is bending moment. Everyone knows bending moment, right? Yeah, everyone is a mechanical engineer, civil engineer, so they should know. Okay, you know, right? Now, when will this system fail? Based on the failure modes, can you tell me when will the system fail? We already did it for cantilever, but now let us see, look into this. I mean, that is because in terms of movement, that's why. Joint can also be in terms of shear force, right? This is in terms of movement, so MC minus. So you just need to know that is in terms of movement, but the limit state is written in terms of movement. That the moment at that point should not be more than some threshold. Now the question is that when will this system fail? We know that when the first limit state will happen, when deflection is more than some limit. The second one is when the bending moment at A is more than certain limit. But when will the system fail? What do you think? Huh? For now, let us say that they are related by P, because both are function of P, obviously. But for now, let us assume that that's not the case. Let us assume them to be independent. So the 2 modes I am assuming independent, which they are not. But let's assume them to be independent. No, that you don't know. You don't know the threshold. I might make a very strong. How do you know that? So I'm not asking how will the system fail. You are going into how. I'm not asking that. I'm asking when will you say the system has failed? If either of them happens, system fail, everyone says that. Is there someone who disagrees apart from me? Everyone agrees. I'm saying no, that will not happen. See what will happen. Suppose the moment is exceeded. Because of that, the joint will fail, right? But how will the joint fail? It will fail to carry the moment capacity. It will not be able to carry the moment, right? Right? But that joint was not only supposed to carry moment, that was a fixed joint. Moment was one of the degrees of freedom, or one of the things it was restraining. There were other things it was restraining. What was it restraining? Forces in two directions. The other one I've not shown, but so what happens when I have a fixed joint that cannot carry moment? What do I get? Simply supported. So when this fails, this will be converted into a simply supported, which means even though one of the failure mode has happened, and apparently it seems that failure due to moment will, one of these would result in failure, but that does not happen, because when it is failing only because of moment, that means in a practical sense that that joint no longer can resist the rotation. Because earlier it was resisting the rotation, now it will not be able to resist the rotation. So what will happen? That will rotate, but that is fine. Previously the deflection shape was something like this. Now the deflector shape will be something like this. But that is not a failure. It can still carry load. If you keep on increasing the load now, and then if it fails in carrying this deformation, then it's a failure, because then this is alone and this is nothing, there is nothing to support, this will keep on rotating. So now it is not able to carry any load. And this is something not new. This is what you study in degree of indeterminacy. That for something to fail, the degree of indeterminacy first has to come to 0 and then it has to go to negative. And only when the degree of indeterminacy go to negative, then you call that it is now no longer in equilibrium. It will keep on moving if you give any small load. It will not be able to carry any load. You are having some question. Correct. Your purpose is defined that this should be able to carry load. Generally, that is the purpose. This is not cantilever, by the way, but yes. Yes, but that is generally not the purpose. I can take it one step ahead. So I was saying that the joint was defined in terms of moment. Let us define the joint in terms of shear force or reaction force, but at the right end. What will happen if that fails? It will become a cantilever beam now from propped. It will still be able to carry load. Same thing, same story. Which means this, and this is happening why? This is happening because this was a redundant system to start with. This was a system, the degree of indeterminacy was 1. So first the degree of indeterminacy has to become 0, statically determinant, and then only it can fail. Which means it is not so straightforward and you cannot do it mathematically. Engineering knowledge is absolutely needed to come up with even defining what this failure means. So that is why I have used the term redundancy. Redundancy means that the system is redundant to start with. You have given additional members, so that even if one member fails, the remaining members will be able to sustain the load. And that is what we generally do. We build building, we build bridges, everything are redundant. We never make it that if one member fails, the bridge will fail. We always design it in such a manner so that even if one member fails, the bridge is able to carry load. I'm not saying it is a series thing. I was saying it is a series thing. You said, and I agreed, when it was a cantilever beam. I'm not said that.
We can, our objective is to carry the load, right?
Yes. Your objective is always to carry the load.
Main objective is to carry the load.
What is the objective of making a beam? What is the objective of this beam? Apart from carrying load, what is the objective?
Objective is something different.
Example. Example.
जैसे यहाँ पर हम लोग का
Example that what can be the objective of a beam.
is to carry the load.
So then what you are saying is redundant. Now you are adding a redundancy by spending 1 minute on saying something that is obvious. Now you are redundant now. What is the objective of a beam?
See, I mean, we are defining the limit state function.
Yes. Yes.
Okay, so our objective is not to fulfill this. Main objective is
Our objective right now is nothing. First of all, our objective is to explain system reliability. First of all. Now come back to the real problem. That was a joke. In a real, our objective is to understand what does it mean for a system to fail. That is the objective. When I say a system will fail, what does it even mean? Does a part of system failing means the system has failed? Does one failure mode satisfying means the system has failed? No, in most cases. Our objective is to understand what failure means to a system, so that we can take an engineering decision, a knowledgeable decision as an engineer, to define what the failure modes are and what failure means. That is the objective, right? The objective is to understand what failure means. Because, see, MCS, surrogate model, form, SOM, all of these are tools. These tools only act along with some limit state function. That limit state function will be defined by an engineer like you and me. I mean, I cannot claim I'm an engineer any longer, but yes, I did engineering, right? So that's how I came here. But it will be decided by someone like you and me, right? So you and me will decide what failure means, with the help of codal provision, obviously, but you and me will decide, correct? So that's why it is important for us to know what failure means. Now, in this scenario, you don't need to know anything, common sense. What are the objective of beam? To carry load. What is the objective of slab? To pass, or I mean, generally the load objective of beam is to pass the load to the columns. The objective of the columns is to take that load and pass it to the foundation. And foundation is what actually carries load, if I have to go in that manner. But generally speaking, beam, column, everything is taking load. Even slab is taking load. But then there is this wall, it does not take load. Or rather, you don't design it to take load. It does take load, but you don't design it for it. You assume it will not take any load, the walls. But these beams and columns are supposed to take load, right? We'll come to that. That is next lecture, maybe not today, but we'll come to that, right? But yes, I mean, you have to use your engineering judgment to answer it shortly. Otherwise, you cannot do that, right? So redundancy is important. You will try to make a structure, system, component, if possible, in some cases, redundant, so that you have a backup. And sometime, I did not. So when it becomes from that to this, you will feel more deformation. That is also an indicator for calling for maintenance, which means this is also an indicator that, okay, it has not failed, but it is towards failing. Why not you maintain it? So it is also a signal towards that. So there is a maintenance is an integral part of reliability. These are not decoupled things, they are closely coupled. So when something happens like that, it is an indication, go and maintain it. Maybe add some two more support or something like that, right? Any doubt? Not true. Not true. That's if that was the case, I would have covered this and then gone into system reliability, reliability under design, design under uncertainty. So reliability, it is not true that reliability will only do during design. Yes, one of the primary aspects is you do reliability during design, and you should ensure that. But you should also keep on computing reliability throughout this time period. That will give you a sense when to maintain, what is the remaining useful life, what is the structural health, and all of those things. So all of those are related. So it's not true that you only do it, but yes, Doing reliability for design purpose is one of the main goal, I will say, or main objective, right? And that is why you will see that in most cases we are talking about simulator, till now at least. But when you will go for reliability of something that exists, you have to actually go to collect data, and the reliability should be based on those data in that case. It cannot be only based on some black box simulation which you don't understand. So the way I have taught it till now, because the aim was to reach reliability based design optimization. Yes, until this point we were talking about simulators because that was at a design phase. Now it is still at a design phase, but you can also use it at a maintenance phase. But if you are doing it at a maintenance phase, then real data has to come. Otherwise, it will not work. Obviously, there will be changes and that has to be carried out. The easiest way to do that is you do measurement based on that, update your model. Now use your model to do reliability. Even in that case, that is the whole step. You will take measurements, solve an inverse problem to update your model known as finite element model updating, and then use that updated finite element, combine with surrogate or whatever you want to do reliability for time dependent, by the way, in this case. Okay. So redundancy is important. Third thing that is important is, I spent 45 minutes on this. The third thing that is important is, and this I have already discussed, is correlation between failure modes, right? And this is kind of obvious because if I have 3 modes and let's say I want to find out this is what I was saying. This is, I know, is equal to A plus B plus C minus AB minus BC minus CA and then plus ABC, something like this, right? It looks like this, correct? So if it looks like this, then you can understand that we need to calculate this once, right? Which will depend on how the failure modes are correlated or how they are statistically dependent or independent or whatever, right? So that is important. That is kind of obvious, right? So that is also very important. There are additional things, but maybe let me start quickly with how will you do or solve a problem that is something like this. There are 2 ways. Let me just tell one, the other one I will tell tomorrow. Even the one I am telling today, I will again repeat it, not tomorrow, the next lecture. One is fault tree approach. So one of the way of doing system reliability is fault tree approach, where you look at different paths in which failure can occur. Okay. In fault tree approach, you define different paths in which failure can occur and compute probability of failure through each of these paths. Now these paths are obviously going to be independent. So then whatever path is having the highest probability is your probability of failure. So one of the ways, fault tree approach. So here the idea is that identify different failure paths, right, and use that for computing PF. So I'll give one example and that will take 5 minutes and then we'll close, okay, of this fault tree approach, not fault tree but failure path. Okay, let us take something like this. And this will also lead to some of additional points here. Okay, I'll show you how. And this, okay, and let's also add member because we don't have any work, so let's add, make it complex. Okay, how many members are there? Let me also add this one. Okay, so now let us number the member: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, clear? What will happen? Okay, I want to reduce it. Let me reduce it slightly. Okay, because otherwise it will take time. Okay, so member 5 does not exist. Let's assume. Okay, because then I can show it easily. So suppose member 3 fails. What happens to the system? It will collapse. So that means one failure path is that 3 fails. Okay. Member 4 fails, 3 is there. If member 4 fails, it will not collapse, right? But up 4 fails, then 3 fails. Then, so the second path is, then 1 fails. So the third path is 1. 4 fails, then 1 fails. Collapse. 2 fails. It need not collapse. If these joints are strong enough, it need not. So 2 fails, and then 1 fails. 2 fails, then 4 fails, then 1 fails. You can understand how many parts there can be. And I can start from the top I have not even touched. Because if I touch the top, then there is 6, 7 and all those things will come into picture. What? Obviously combinatorial here. But this also gives an idea that when we are designing, now comes design, we should design so that the failure should occur through the longest chain. So you should design in such a manner that it should fail using the longest chain. Because then, even if that probability of failure is little bit higher, because there is a chain, when one thing fails, you get a warning. Because warning is also important. Now, to continue on this, each of this will give you a probability of failure, right? Whatever is the maximum probability of failure out of this is your probability of failure of the system. So this is what you will do in fault tree approach. So identifying the failure paths become very, very important. If you miss one path, you will start underestimating, which is bad. You can overestimate but not underestimate. So if you underestimate, that is bad. So that's a limitation of fault tree. Fault tree approach is good when the failure is ductile failure, because you get enough warning and all of those things. For brittle failure, this is not a good idea. Okay. For brittle failure, you do the opposite of that. You look into what are the different ways the system can survive, and combine them to find out the probability of survival. 1 minus probability of survival is equal to probability of failure. So in fault tree, you find different ways the system can fail. In the other one, which is safety based, you analyze different ways the system can survive. And in that case, it will be a union. In this case, it will be an interest. I mean, in this case, it is a union. Like if one fails, everything else will fail. In that case, all those survival has to be there. So you will calculate the probability of survival, and that will actually overestimate. So that is a safer one. But that is generally preferred for brittle. This is for ductile. One more thing when you're designing. So let us see. If this member 7 fails, will the system fail? No. Common sense, right? But now imagine this is a building. What happens after 7 has failed? What does failing of 7 means? Again, the same question. If it means that it has deflected enough, but it is still carrying load, but we are defining it as failure, then it's fine. But if it has failed and collapsed and fall on the floor, then first of all, whoever is staying on the floor will die. Second, because of it falling, there will be an impact, and because of that, now the middle one will fall, and because of that, everything will fail. You have to also be careful about defining failure. Whether defining failure you mean that because the deformation is more than certain factor, that's why I'm defining it as failure. Because it has collapsed, that's why I'm defining it as failure. Because if you're defining collapse as a failure, then that is a high risk scenario you are creating. You should not do that. That means the progress, how much, performance of a member after we have declared it failed is also important. Because whether it is continuing to carry load but has deflected more, we are calling it failure. Why? Like the wall I said, wall carries load, but we design it assuming it will not carry load. It adds a redundancy. Yes. 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 So the idea is that performance after a component has failed, or rather you can say that post failure behavior of a component. If the post failure behavior is fine, then it's fine. If it is not, yes, if 7 fails, we know that the system will not fail, but if it crashes, we know it has failed already, right? So that means one has to be extremely careful when defining these failure parts. Think about all the possibilities in which it can fail, incorporate all of those, and only after that whatever tools we have discussed will come into play. And when you try to combine all of those, you will realize you now cannot compute it, so you need assumption. So then you do the lower bound upper bound thing, everything is correlated, nothing is correlated, come up with those extremes, right? We'll stop here. Yeah, we are out of time. Next lecture will start from this, and the idea is to complete this system reliability. Obviously, you can understand the way, it can be a course of its own. If I go into all the failure modes and start talking, it's a course of its own. Obviously, we will not do that. What we'll do that was that to introduce you to what failure means, what is system reliability, and then some basic way of doing system reliability. Okay. No, health monitoring will not do, because this is not a course on health monitoring. But reliability is used for health monitoring as well. That's what I meant. You have to consider, right? As it with time you have to consider. But right now I'm talking about design only. Again, throughout this course I have focused only on design, as you were saying. But what I meant was that it need not be only for design. We are focusing only on design because of it's a course. Because I have only 14 weeks. Because I can have a limited syllabus. But does not mean that is the scope of that subject. That is the scope of the course. It's a 1 semester course, right? That's what. Okay. As I said, system reliability can be a course of its own. Gaussian process can be a course of its own. Many of these things I've covered can be have their own courses. Okay. Thank you.